In this video, I want to provide some practical information that will enable you to find some of the information you might need to answer some problems. And in particular, this information is stored in something called a pKa table. Now, pKa tables are available in lots of different places. I provide a few through the course, which I'll show you presently. But you should be aware that, in fact, a lot of this information can be found also just by doing random Google searches online. So let's get started. We're going to have for learning goals to extract meaningful information from pKa tables. All right, so the main information we're going to need is the result of the equilibrium constant for these reactions. The top reaction is the weak acid dissociation reaction in water, for which the equilibrium constant is Ka. Oftentimes this is reported as pKa, which is of course the negative logarithm of that equilibrium constant. We may also be interested in the base reaction, the base equilibrium, which is the second reaction. I've shown it here for the base that's conjugate to the weak acid HA, but you could also do it for any base. And in fact, what often happens, and we'll talk about this a little bit, is that when we're talking about the basicity constant for a base, instead of reporting that, they'll report the Ka for its conjugate acid. All right, now the main ways that you find these tables organized, and there's several different ways they can be organized. They could be ordered in order of acid strength. They could be placed in alphabetical order by the name of the acid. They could be in numerical order by formula, or they could be in separate tables for both acids and bases. You can find all of these different ways of organizing them, so you need to be alert and figure out for the particular table that you're looking at how to find the particular acid that you're interested in. Now, I want you to remember as you go through this that when you look at these entries, that if it has a large pKa, that means it is a weaker acid. Small pKa corresponds to stronger acids. The same would be true in case of bases. You won't find pKb's listed too often, but if you do, a larger pKb means a weaker base. Now, as I mentioned, often the pKb of a base B is reported really as the pKa for its protonated form. You convert it to the acid form and report the pKa. So that means you're going to need to be able to convert back and forth between the pKa and the pKb of a conjugate pair. So I want you to remember this relationship, that the product of the two always equals Kw when we're talking about things in aqueous solution. All right, so now let's switch over and see if we can see what these tables look like. So here's a shot of our course site in Blackboard, and you'll notice all of the things that we have here in the left column. One of the items here is called chemistry resources, and I do want you to avail yourself of these as often as you can. So I'm going to go into the chemistry resources, and some of these are files that I have put there as part of this course. These are the ones marked in blue, but then there are some that are just online resources, and these are the ones that I want to go to today. One of the first ones there is the acid dissociation constants, the pKa values. There's also some listed here in the data tables by Reusch, and so let's go to this one first. So here is a pKa data table, and you can see in this particular case these acids are listed by formula. So you have to be a little alert to see that, but here's the number of carbons in this column that are in each of these acids, and here's the number of hydrogens, the number of oxygens. So if you use this table, you really need to know the formula of the acid that you're interested in so that you can find it as you look through this table and find its values. Now here, the pKa values are listed along this column. And remember that the larger pKa is, the weaker the acid. So for example here, trifluoroacetic acid, that's a pretty strong acid because it's got a very small pKa. But something down here like, what is this, propionic acid is a little less strong. And isopropyl alcohol is not a very strong acid at all. It's got a pKa value of 17.2. Now, some of these also have a second pKa listed here, and that tells you that this is an acid that has more than one acidic proton. It will lose one proton with this pKa. It will lose the second proton with this pKa, and you'll notice that the second one is always larger than the first. It naturally follows. It's got to lose one first before it loses the second one. All right, so let's look at a different format for these pKas back in our course website. And I want to show you what Royce does for this. So when you click on that one, you end up in a page that has just a bunch of useful tables. It won't take you directly to the acidity constants, but you can find them over here, organic acidity constants. And the way that he organizes these is really by order of acidity. So we're going to get more and more, or sorry, I should say less and less acidic as we go through here. So we start with the strongest acids at the top and we work our way down to the weaker acids. Now this table, as is the other one, it's limited in terms of how many acids it includes. So you may not always find the one that you particularly want. And if you can't, another useful remedy you can have is to switch over and do a Google search for the acid that you want. So for example, I've done that here for butyric acid. If you just do a search on butyric acid pKa, it will quickly come up to this. It'll give you some different sites where you can find out about butyric acid, and you can get the pKa directly. If all you're interested in is one pKa, I would say rather than looking through a bunch of tables, go to Google and just do the search. However, if you're interested in comparing a number of them, it's useful to go to a table and compile them so that you can look at a bunch of them at one time. So I hope that helps you learn how to use pKa tables. If not, ask questions.